طيب بسم الله الرحمن الرحيم. So in chapter 4, we started to talk about the network layer. We talked about the difference between routing and packet forwarding. And then we started to talk about the two philosophies or the two major architectures in the design of the core network for the internet, namely the datagram architecture, which is the predominant one, and the virtual circuit. As we said before, the datagram is built around the philosophy of making the core network simple and pushing the complexity towards the edge network. So more complexity in TCP or in the transport layer to control the flow, to control the congestion, to provide reliable transfer and so on. And this will be done at the edge, end to end. With that, we can keep the core network as simple as possible. And that's meant to be like this for promoting scalability. Okay? So we don't have to provide virtual circuits. We don't have to provide circuit state. We don't have to maintain a state for each circuit at the core network because we have millions and possibly billions of them. So maintaining a state for each virtual circuit, establishing these virtual circuits at the core network level is not desirable for scalability issues. But with that comes a specific cost that, as we said, the type of service that you can provide for datagram architectures is elastic. Elastic here means that you cannot have any guarantees on the service. Okay, so you cannot have any quality of service guarantees per se, or it's hard. So there are some techniques to provide quality of service on top of the datagram architecture. However, it's very hard to provide this type of quality of service guarantees, and even then, it's not going to be an exact quality of service. So you can control it in a way, but you cannot provide 100% guarantees. Let's call it this way. Okay. So again, it's built on the smart end systems. So the smart end systems, which are represented by the transport layers of the two edge networks, they provide all the error recovery, the flow control, error control, and congestion control. And the core network itself is simple. Okay. The virtual circuit on the other side, they evolved from the telephony system. The public switch telephone network initially used what we call circuit switching. So circuit switching evolved in the network layer as virtual circuits. By circuit switching, we mean like for each phone call end to end, we have to establish a physical circuit. But for the network layer, we can do similar approach, but in that case, we call it virtual circuit because it's not a physical connectivity per se. It's just a logical route end to end. So with the establishment of these virtual circuits, there is an overhead because you have to do some signaling for call setup, okay, before you start communication. And then this will allow you to provide exact quality of service guarantees in that case. However, this has lost ground a great deal because of what? Because of scalability issues. IP has become the predominant protocol on the internet. However, later on, for some specific networks, they provide a very interesting protocol which is called MPLS. So MPLS works underneath IP. We're not going to cover this. I'm just saying. So MPLS works under the IP protocol to provide circuit-like behavior. Okay? It's similar to the fact that when we said UDP does not provide anything, so if you need to provide flow control and error and congestion control, what would you do? You have to have a protocol on top of it to provide the flow control and congestion control that you need to have, right? This is in a way similar. And MPLS is not deployed in the core network of many infrastructure networks. So for some specified network infrastructures, sometimes they use MPLS to provide circuit-like behavior, especially for organizations or network infrastructures that require quality of service guarantees. But anyway, MPLS, we may actually cover it at the end superficially, but that's not the main topic of this course. Okay, so this is the main difference between the datagram architecture and the virtual circuit architecture, and that gives you some indication that developing architectures is an art. It's very important. So to really think about developing the architecture philosophically. So the main philosophy of the difference between datagram and virtual circuit is the scalability. And that's one of the main features of the internet. And that's why, even though datagram architecture is very simple, but it's the more dominant. So sometimes simplicity is needed, okay, to provide scalability. So with the proliferation of مثلا software-defined networking and virtual network functions and so on and so forth, these types of circuits and stuff has been, the control for these circuits have been pushed to the cloud. And that actually might change the mindset completely. So maybe, at some point, maybe you can establish some kind of virtual circuits at the core network, but the control for this is done at the cloud. And that's what they are trying to do as part of the SDNs and things like that. So now, the topic of today's lecture is mainly to try to take a deep dive inside the router. So we'll open the router, we'll get inside, and we need to talk about the architecture inside the router, how the router is really, how does it work from inside, what are the main components. And again, in that case, so we'll talk about the computer architecture design of the router. So we'll take a look at different architecture designs inside the router. We'll talk about the pros and cons for each of these architectures. So this is the overall architecture of the router. So you have, these are input ports, and these are output ports. And here we talk about the switch fabric. By the switch fabric, we mean that from the input port, the packet gets stored. So we'll talk about the details of this. And then you need to process the packet. The main thing is that this packet has a header, and in the header we have the destination address. And this is the most important field in the packet, right? So using this destination address, we need to consult or look up the routing table, and based on the routing table, we need to make a decision that this packet needs to go from a specific input port to a specific output port. That's done as a hardware inside the switch fabric. So this switch fabric itself needs to facilitate the switching, the physical physical switching as a signal from one input port to one output port. Okay, so we need to talk about the function of input port, the output port, what are the differences in terms of functionality. And then the main brain of this router architecture is what we call the routing processor. And in the routing processor, we have the embedded software. Okay, This embedded software is is where all the intelligence is. Okay? So this routing processor controls this hardware to say, okay, so the packet needs to go from this input port to this output port. That decision is made here. So if we were to divide this into two parts, this is what we call the forwarding plane. Okay, the forwarding plane is done purely hardware. كله hardware. Okay. So the input ports, output ports, all of this are hardware chips, hardware components. Okay. And that's the control plane. This control plane runs as embedded software that runs on the processor. And this embedded software is the brain of the system, as we said. Okay? A processor runs like a low-level operating system and software that controls how the routing is done, how the lookup is done using the routing table, okay? And how the switching is controlled, okay? So this is basically the brain of the system. Okay, so now again, doing some analogy between this design and what we have nowadays in terms of cloud computing and SDNs. So what they are trying to do is to push the intelligence to the cloud. So the control plane is partially or totally pushed to the cloud. So this will be done at the cloud. So you don't need, you need to have a routing processor still, but this routing processor is relatively dumb in that case. So most of the intelligence in terms of how to produce the routing table, how to control the functionality of all these hardware is mostly pushed to the cloud. Okay, but the forwarding plane has to be done in hardware, and we'll talk about why this is the case. Okay. Of course, first and foremost, to maintain like fast processing. So if we take a zoom in into the input ports, of course, needless to say, in the actual routers, ports, they work as input and output at the same time. So each physical port can act as input and output. And again, this is controlled by the processor. At any point of time, you can control a specific physical port to work as an input port or as an output port. But physically, any port can act as input or output port at any point of time. ماشي? So the input ports, they have 3 blocks which align perfectly with the 3 layers that we have, because as we know, the router has physical layer, data link layer, and network layer, right? So these blocks, they correspond to each of the layers. Okay, so they align perfectly with the layers. So we'll see the line termination. This is basically the physical layer. And here in the physical layer is where all the channel estimation, the conversion from analog signals to digital bits and so on. Okay, so this deals with the physical medium, and then what I get here is a set of bits, digital bits, zeros and ones. Okay, so line termination performs the channel estimation, the signal detection, and all of this. Okay, and then it converts all the signals, whether it's a digital signal or analog signal. It converts all of this into bits, and then it feeds that to the link layer part. The link layer part, طبعا, it performs the data link layer functions, including the طبعا the error control at the data link layer. Of course, these bits will be converted into here frames, okay? So you have to have the frame start, the frame end. You have to detect the start and end of a frame. Of course, here also we have to account for collision, whether we have the medium is collision based or collision free, and so on. So we have to perform all the data link layer functionality at this level. ماشي? And then here is the network layer. This is the main focus. So in the network layer here, at the input port, what we need to do is we need to queue the packets, okay? And again, why do we need to do queuing? In architectural design, you need to have a queue or any kind of buffer if you have an input process and an output process which vary in terms of speed. So basically, you have no control what is the inter-arrival time of the incoming packets, right? However, here, the service time of each packet is limited, right? So, for example, here, you have a service time X, but the line speed can be less than X or more than X at any point of time. You don't have control how the packets are coming in. So that's why you need to have a queue, right? So this queue stores the incoming packets, and then you have the service. Here the service is what? Each packet we need to look up the destination address, and then we need to consult or to look up the
forward to a specific output port.
Right. So we need based on the destination address. We'll talk about the design of the routing table later on. But so the processing of each packet has a limited time, and that's why we need to have a queue. Okay. So there's also one important thing here, is that the lookup speed has to be done very fast, and this is one of the reasons that so all these components are done purely in hardware. So we cannot afford the fact that you take a long time in terms of how to process the packets. So processing the packets and everything is done, and to speed up this process as much as possible, what they do is that they do a shadow copy of the routing table at every single port. Yeah, so that's yes. So this is done specifically to try to speed up the processing of the packets. Okay, so this is purely done in hardware, and that's why we call it decentralized switching. Decentralized switching معناها إنها we keep the lookup process independent at each input port, because, well, as you know, the routing table has all the input ports and all the output ports, right? So ideally, I need to do the lookup at the routing table in a centralized location. But because of the fact that the lookup and the switching has to happen very fast, they do it in hardware, and the way they do that is by creating a shadow copy of the routing table at every single input port. Okay. So there is a complete input port processing at line speed that's done in an independent way at every single input port. ماشي? So again, so the input port facilitates the variation in terms of speed between the line speed and the service time. Okay, in terms of the time that you need to process the packets, and they do that using like the queuing system. And as we will see, at the input port there is some kind of queue. At the output port there is another queue, and the queue at the output port has different functionality altogether. So we'll talk about that. ماشي? So this is the functionality of the input port, and as we said, these three components, they align perfectly with the three layers that we have: physical layer, data link layer, and the network. Now, we talk about the switching fabrics. Okay, so to take a zoom in again at the switching fabrics, we have three major architectures, okay, for the switching fabrics. We have the shared memory architecture, we have the bus architecture, and we have what we call here the crossbar, or what we call the Banyan networks, okay, which is basically based on a grid of interconnected buses. ماشي? So we need to talk about the pros and cons of each of these architectures. So, of course, here the switching speed has to be very fast, and sometimes much faster than even the line speed. Okay? Why is this? As we will see. Why is this? Because basically, sometimes you have packets here at different ports that all of them, they need to go to the same output port. Okay? So if the switch fabric works at the line speed, the overall speed of the system will be very low. Okay? But if the switch fabric is much faster than the line speed, then you have all these flows. They go to this output port with a relatively better speed to maintain the end-to-end speed of the entire router from the input port to the output. And remember here, if we're talking about gigabit Ethernet, or very fast speeds like 10 gigabit per second or something. So just to imagine, with this a bit of numbers, if you have a packet, let's say a packet which is 128 bytes only, and this is a very short packet, by the way, very short. Okay, 128 bytes. This is مثلا 1024 bits. ماشي. If we're talking about 10 gigabit per second speed, if we need to maintain a 10 gigabit per second speed, right? What is the service time in that case? What is the service time? It's actually 1024 divided by 10 to the power 9, which is in that case 102.4 nanosecond. Yani 100 nanosecond. Okay? So a packet needs to be serviced in one, and this is the end-to-end service time, which includes the lookup at the routing table, the switching, the output port queuing, and all of this. So if we need to maintain this amount of speed end-to-end, like 10 gigabit per second, okay, this is for routers, this is very fast, right? So we need to have a service time of around 100 nanosecond, which is very challenging if you consider that this includes the queuing at the input port, the switching time, and the queuing at the output port, and the lookup, and so on. Okay, so that's why the forwarding plane has to be purely in hardware, and not only that, even routing table has to be shadowed in all these input ports, because we cannot afford the fact that we have to consult a centralized system to do that. Okay. Type. So this is what we have here. So switching rate, the rate at which packets can transfer from inputs to output, often measured as multiple of input and output line rate. And that's because of the fact that some packets on multiple input ports, they need to go to the same output port. So if you want to have the same speed end-to-end, you need to speed up the switch fabric significantly. ماشي؟ طيب. So what are the major architectures in the case of switch fabric? We have the shared memory architecture, and we have the bus architecture, and we have the crossbar architecture. So So we'll talk about each of these and the pros and cons of each one. Here, so you have like shared memory locations for each output port. So if I need to send the packet to this output port, then I need to write it here, or here, and so on. Okay. So the first one is what we call the shared memory architecture. In the shared memory architecture, what you need to do is that you need to, of course, when you look up the routing table, you decide that you need to send the packet, okay, from this input port to this output port. So that's what you need to do, okay? So the packet needs to go here, right? So the way this is done on the shared memory is that in order for you to forward or to switch a packet in a specific output port, there is a shared memory location for this particular output port. So the memory itself is divided into certain locations, okay, for each output port. So if you want to switch a packet to this particular output port, then you need to write it in this shared memory part, okay? So if the memory architecture itself as a shared memory commonly is based on single access, okay? So in many of the routers, especially the old models like this Cisco Catalyst 8500, this is like the early days of the router architectures. So the memory is single access, which means that first you need to write, okay, and this is one access to the memory, and then you need to read, and this is another axis of the memory. So it's done on two steps. So if you have a memory access time, let's say A, okay, so one packet switching, okay, will require 2A. Okay, so you need two access to the memory in order to provide the complete packet switching. Of course, this limits the speed. Okay, and that's why in today's routers, they came back to the same memory architecture. However, they used a totally different memory architecture which supports multi-write, multi-read, concurrent read and write. So if you have concurrent read and write, you can concurrently write to different locations in the memory, okay, and read both at the same time. Okay, so but that's a very sophisticated memory architecture, which is it's done recently. Okay, so the recent routers, they came back to this architecture, but they use shared memory architecture with multi-read write access. Okay, so in that case, you can write from multiple input ports to different locations in one shot, and you can read from multiple output ports also in one shot. But the old architectures, they did not support that, so they need two accesses to the memory to provide only one packet switching, and that limits the speed considerably. To get around this, they have what we call the bus architecture. In the bus architecture, you don't have to have two accesses in that case. When you forward, okay, when you forward the packet on the bus, anyone can read. Okay, anyone can read. So you can read at any point of time. But to control who will read, okay, we have to add, so this is the packet, and this is the destination address. So here in the bus architecture, they need to have an extra slight overhead. So they need to provide what we call a label. Because if once you put the packet on the bus, anyone can read it. Okay? So you have to control who should read it. And inside the switching fabric, we cannot use the destination address anymore, خلاص. So instead, what we do is that we put a label, of course, which is based on some specific registers in terms of hardware and so on, which allows only one output port to read from the bus. ماشي? So adding this label is an overhead. But this eliminated the two axis time issue which exists in the memory architecture. So in the bus architecture, we don't need to have two axis times. So we can do that in one axis. However, we have to have this overhead in terms of label to facilitate the switching between the input port and the output port. And also, we have to control one input port to have access to the bus, as you can imagine, صح? So one input port needs to have access to the bus at a certain point of time. We don't have collision here though. Why that? Can you think of يعني طبعا احنا any bus architecture we talked about the fact that we can have collision صح? In Ethernet صح? In Ethernet we said that we may have two people writing at the same time, so we have collision, right? But here we don't have collision. Why? Because we have collision if these input ports, they decide independently when to write on the bus. But this is controlled by what? By the routing processor. So the routing processor is a centralized controller inside the network, inside the router architecture, right? In Ethernet, the problem is that Ethernet, you have independent nodes, and they decide independently when to write, صح? You cannot really have a centralized control, because that's the whole point of Ethernet, is to get rid of the centralized control when each one can write on the bus. And we have this asynchronously. So any node can write on, طبعا in that case it's not a bus, it's a shared medium. Any node can write on the shared medium at any point of time because of the decentralization, because each one can take the decision independently. But here we don't have this issue because it's inside the router, and the routing processor allows only one input port to access the bus at any point of time. So we'll never have collision. تفضل.
The routing processor in the previous architecture
Yes.
didn't override the memory places?
ما فيش override because output ports, they have, each one has independent and يعني totally separate.
Input ports are trying to send to the same output port.
Yes, of course, because it's طبعا the routing processor allows only also one input port to write to the shared memory at any point of time, because the shared memory has one access, single access only, for any input port or output port.
I'm just thinking like if one input port finished writing, but before the output port actually finished reading, then another input.
Oh, of course, yes, okay, that's a good point. Yes, of course, the routing processor controls that, so it has to allow the output port to read before another input port writes to the shared memory again. Okay, so it's one single input or output access to the shared memory. Okay, so that's why we say that the routing processor is the brain of this whole system. It controls everything. Here, contention is not a collision. Huh? There's a difference between contention and collision. Contention does not necessarily mean collision. Contention يعني إيه? Two people are contending or racing to access something, but that doesn't mean that they will access it at the same time. Okay. So as you can see here, the switching speed is at 32 gigabit per second bus. Okay? So does that mean that the line speed is 32? No. Because as we said, the switching speed has to be much faster than the line speed. So this 32 maybe will not get you more than 10 gigabit per second. يعني at the maximum. Okay, but because of the fact that the input line speed, each one is 10 gigabit per second, you may have 3 input ports trying to write to the same output port. So in order to maintain the 10 gigabit per second, you need to have a much faster switching speed. مفهومة كده؟ ماشي؟ So in order to get rid of the fact that the routing processor can give one input port to have access to the bus, there is another architecture which is what we call banyan networks or crossbar. In the crossbar here, we have a grid of buses which are interconnected. So now we control بقى which أولا here there are two benefits here. Okay, one, we don't have to provide labels with the packet. Okay, we don't have to provide labels here. We can control which input port sends to which output port by controlling these intersection points. Okay, so the routing processor can light or activate one cross or intersection point to allow this input port to go to this output port. Okay, so this is done by controlling these intersection points. So that's one. So I don't need labels. Another benefit here, which is the fact that I can activate more than one intersection point at the same time, so which allows multiple input ports to write to multiple output ports concurrently at the same time. So I can do that like by activating مثلا this point and this point and this point. Okay? So this means that this will go here, this will go here, and this will go here. All of these are done in one control, in one axis. Okay? So here, this banyan networks, of course, by that, the switching speed has been increased drastically, at least 2 times. Okay? So, and I can do that without having to have, of course, I have to pay a cost, of course, which is, of course, the hardware architecture is much more sophisticated in that case. I have to build that banyan network in hardware. Okay? But this will allow the routing processor to control these intersection points أولا without having a label. ثانيا, I can allow concurrent switching for multiple packets all at the same time. واضح ولا تمام؟ ماشي كده؟ Okay. So in order to do that, in order to facilitate this and also make the speed very fast, they have opted to use fixed cell length. And the reason for this is to have, because of course, for the packets to be switched, if you have variable size packets, okay, so the switching for each packet will take a different time. For a packet to go from here to here, you take a different time depending on the length, right? So they found that if they make the packet length fixed, so the speed of the entire network becomes higher, because the switching will be done for all these fragments of the packet will be done at the exact same time. So this allows them to have more concurrent intersecting switching at the same time. Okay? So in order to do that, they have to make the datagram of fixed length or fixed length. Okay? So that's one of the costs that you have to pay. إذن الcost هنا, one, of course, the hardware architecture is more sophisticated because of the fact that we have to build this interconnect or the banyan network. Another thing is that you may have to do actually cell fragmentation inside the router. If the incoming packet size is variable, you may have to cut and keep the length of the packets equal. ماشي? So, but this will facilitate this very, very fast switching speed. Okay? Any questions in these three? So we talked about the shared memory architecture. It requires single read or write, and that lowers down the switching speed. So to speed up the switching speed, we opted to use the bus architecture. However, the bus, it's a shared bus, so you have to label where the packet is going. So we have to provide a label with the packet to allow only one output port to read from that bus at any point of time. And in order to facilitate concurrent packet switching, we also talked about the Banyan network, where we have crossbar architecture that allows multiple input ports to write to multiple output ports at the same time. And we do that through controlling the intersecting points between the input ports and the output ports. Okay? Any questions? I have to say that for each of these architectures, by the way, there are different variations. But we don't have to talk about the details of this. So for example, مثلا for the shared memory, we talked about the variation. So we have the shared memory architecture, and the recent architectures, they use the shared memory, but the memory itself allows concurrent read and write. So that's another variation within the shared memory architecture. In the bus architecture, we also have some architecture that uses label with the packet, some architectures that uses some other approaches to facilitate the bus access between the input and output ports. And also with the Banyan network, there are some architectures that allow multiprocessors, okay, to control these intersecting points and so on. So there are some variations within each category. ماشي؟ طيب. So after achieving the lookup at the input ports, and the packet, alhamdulillah, has successfully arrived at the output port, okay? So at the output port, what do we do? So at the output port, we have to, again, perform the 3-layer functionalities in reverse, okay? So first, we have to do again, queuing. Why queuing here? Why we need to do queuing here? Again, we need to do queuing whenever there is a difference in speed between the input process and the output process. And that's the case here, right? So the switching, okay, gives you some packets with specific inter-arrival time. And depending on the switching, because multiple input ports need to switch to the same output port and so on. So at single output port, you may get packets arriving with different inter-arrival times. So it's never going to be fixed inter-arrival time, okay? Neither at the input port nor at the output port. So that's the input process. So the input process does not have a deterministic speed. The output port also, the output process also does not have a deterministic speed. Why? Because this may be like an Ethernet physical line or wireless, okay? So either Ethernet or wireless or anything, you need to perform sensing on the line, right? So you cannot just get the packet converted and send it right away. So you have to sense. مش احنا اتكلمنا عن carrier sensing multiple access فاكرين؟ Carrier sense multiple access in the data link layer. You cannot just write on the line like this. It's similar to 2 cars getting into the intersection. Are you going to be careful to see if there is anyone in the intersection, or you are going to write, enter the intersection blindly? أنت حر. If you do this, you will cause accidents very often. صح كده؟ So
حتى لو في established connection في حالة ال TCP.
لا TCP فوق، احنا مالنا TCP.
لو في established connection.
لا ملوش علاقة. احنا هنا this router is in the core network. TCP establishes speed for end-to-end connection. احنا هنا the router is at the core network جاي له يعني different traffic from different nodes all over the world جاي له يعني الدنيا كلها جايه على بعضها. انا ما اعرفش بقى جاي من TCP جاي من UDP جاي من ICMP جاي من اي حته، انا ماليش دعوه. Okay, but the difference here is that depending on the physical connectivity here, whether it's Ethernet or wireless, I may have to wait a little bit before I write, right? So not only we have a queue here, we have a queue here as well. Okay, so we have to have queuing. The queuing at the network layer here accounts for the quality of service or priority. So for IP, we have packet priority. كانت فين بقى دي؟ حد فاكر؟
ده في فلاجز.
flags what؟
urgent ولا لا ولا دي حاجه ثانيه؟
لا urgent flag، لا urgent flags ده TCP.
ده TCP.
في الاي بي بقى كان في we had في الاي بي كان we had like some priority for each packet. كانت فين which field؟ الناس اللي بتوع النتورك 1 which field represents the priority of the packet?
We spoke about it with the explicit and implicit.
Right, we remember the explicit congestion notification. كان في واحد بقى على شماله كده وانت داخله كده على شماله كده. اوكي، كان اسمه ايه بقى؟ احنا قلنا في there is a field I will talk about it again today luckily يعني واضح طبعا ان احنا we need to talk about it. كان في حاجه اسمها differentiated services صح؟ فقلنا ده it's divided or subdivided into two fields. One is the explicit congestion notification. If we said that we support explicit congestion, when a TCP does not do that, does not make use of this in any way, right? TCP relies mainly on implicit congestion, which means it doesn't need to take any notification from the network that the network is jammed, and it kind of makes some assumption. مش قلنا كده؟ Okay. So what field is this? اسم هو ده بقى اللي احنا مش okay. Differentiated service code point. It's called a differentiated service code point. Okay, and this is like 5 bits, and that represents the packet priority. Why do we need to have priority for the packet? Why? Because if يعني do we imagine or do we think that the packets coming from different applications, they need to have the same behavior? Of course not. If you have packets coming from a video streaming application, okay, video streaming application requires delay sensitivity, requires its delay, we call it delay intolerant, okay, and it's loss tolerant. So if you are watching like high definition video, if a packet gets delayed, you better drop it. If a packet gets يعني lost كده in the net, you better drop it أحسن. Because dropping one single packet will not affect the quality, but delay will affect the quality. صح? The delay will cause some pauses in the video, and that usually gives very bad impression to the user, right? So it's better to drop the packet rather than delaying it. And that's the main reason we said that TCP usually is not good, it's not efficient for real-time streaming, صح? Because TCP always reflects or always causes delays based on packet loss, because it's 100% reliable. So it will keep retrying to send the packet, and the packet delays get higher. So it's better in that case to drop the packet rather than having to retransmit it several times and cause the very high latency. So on the other side, some other applications like مثلا banking applications, even some kind of web browsing applications or something like this, they require reliability, 100% reliability, okay? And delay is not a critical issue because if you get delays for a few milliseconds, it's not going to affect the quality of service. But losing the packet is very critical. So, for example, if you are transferring like a zip file or any kind of file content, if you lose one packet in that file, this means that the whole file is corrupted, صح? So you cannot really afford that, and that's where TCP بقى will be very useful. 100% reliability is not an option. Okay, so that reflects in the network layer as priorities for each packet. So if I have these packets, I need to do some kind of they do some kind of scheduling. Okay, so scheduling based on certain priority for these packets. So packets that are coming from, like, for example, streaming applications, they need to take very high priority. Packets that are coming from banking applications, they need to provide high priority in terms of loss. We cannot afford losing them. And so on. So sometimes they do that at the output port based on this output port, it's not actually a single queue. Sometimes they use what we call priority queues. So it's not just one queue. So packets, depending on their priority, they need to get to one of these queues, depending on their priority. Okay? And then there is a scheduler here that schedules when to take one packet from each of these queues. And that depends on the differentiated service code point. Okay? So that gives you, again, we said that datagram architecture does not provide quality of service guarantees, but this gives you some quality of service control, صح? But it's not exact. It's not exact. It's always relative. So here, the higher priority will get better than the lower priority, but how much exactly we don't know. صح? So it's not virtual circuits. So by saying that, we don't mean that it's a virtual circuit by any means. So here, the quality of service is relative. And it's not exact by any means. Having said all of this, this differentiated service code point is similar to the explicit congestion notification. IP provides these, but it never defines how they are going to be used, if any. So they are provided as part of the standards, but they don't say about how they are going to be used. It's up to anyone to use them in any way they see fit. So whether you use them or not, and how you use them, okay, you still comply with IP as a standard. So I'm going to provide these fields. If you want to use them, fine. So some implementations of routers, مثلا specific Cisco router models, they use the differentiated service code point to provide some priority for the packets. Fine, that complies with IP. Another model from مثلا Linksys or D-Link or Netgear or something like this, they decide not to use these fields. Fine, they still comply with IP. They can talk to each other. There's no problem. Both of them, they still comply with IP. No, because for input, I don't need to have priorities to switch the packets. I need to have priority at the output port to schedule when the output port will send this packet on the line. Okay?
It will affect the speed because it become more complex.
Complexity because of the multiple queues.
Yeah.
Again, the priority queues or multi-queues is not a requirement. It's not a requirement, but if you need to use or to make use of the field differentiated service code point, one of the designs is to have multiple queues, and each queue will have different priority. And here the scheduler will say, okay, so this is high priority, I will take 2 packets from here and 1 packet from lower priority, and so on. So it serves this queue faster than this. Or it decides that whenever I have a packet in the higher priority queue, I will take it. If I don't have any packet in the high priority queue, then I go to the second, and so on. There are different designs, by the way. This is a big area of research. So to design the scheduler here is a big area of research. Or was a big area. There are tons of techniques, hundreds of techniques.
If the router doesn't use the differentiated service thing, how it will cover up for the reliability need for the application that needs reliability?
It doesn't. ما احنا قلنا IP is not reliable. IP never promised any kind of reliability. Okay? This is the whole point. IP is unreliable, best effort. Okay? Complexity, reliability is pushed to the end, to the edge networks. So TCP بقى ربنا يعينه will take care of this. At the core network, we cannot provide this. But however, as we said that يعني as the internet gets more طبعا this guarantees the scalability of the internet, which is good. However, the fact that we cannot provide any quality of service guarantees is becoming more and more unacceptable. So we need to have this quality of service guarantees. So again, the virtual circuit and the datagram are two extreme schools. ماشي? Two philosophies which are totally at the extreme. One pushes the complexity completely at the edge, and one provides the complexity at the core. And that virtual circuit architecture seems to lose ground because of the scalability issue. Fine. So the other school has dominated, but they are trying to provide some solutions to the pitfalls and the drawbacks that exist in the core internet, which is the fact that the internet needs to have some quality of service guarantees, even if it's relative. It's not exact, but it's relative. And that's one of the ways to try to provide quality of service guarantees, but it's not exact. Remember, because here we don't have any virtual circuit state maintained. So we cannot provide quality of service for a specific virtual circuit because we don't have a virtual circuit state. We don't know where these packets, and we should not know, we should not care about where these packets is coming from. We don't maintain that virtual state inside the internet. And this is by design. However, this differentiated service code point it kind of, provides some guarantee. So the better question is, who sets these differentiated service code points for the first time? ماشي? So that's a question. Again, IP does not. هو بيرفع ايده and I don't specify how this is going to be used. But logically, as you can imagine, this has to be set from the original application. So the application has to specify certain priority that gets embedded in every single packet that goes into the internet. ماشي? If it's ever used, but we do not force anyone to use it. And we don't actually force how it's going to be used. Okay? So, for example, مثلا أريد مثلا if they want to provide like مثلا video on demand or triple play مش عارف إيه لما. So, in that case, as we can imagine, we need some quality of service guarantees because we need to make sure that the traffic encounters very low delays, because delay is critical in that case. Otherwise, in our houses, we have مثلا أريد TV ولا حاجة زي كده. We see like the video pauses every now and then. And now it does يعني every now and then it pauses صح, as we can see. However, يعني with some quality of service implementations, these أريد TVs can give you some kind of quality of service. But it's not guaranteed, it's not exact. And that's why for every now and then you have some glitches. Because that's what the internet is designed to do. It's highly scalable, and depending on the network state, you may have some traffic jams at a certain point, in which case you have some pauses in the video. When it happens, if it happens, we don't know. We don't have any exact guarantees. Anyway, so يبقى احنا عرفنا, so at the output port we have still the queuing, and the queuing at the output port network layer provides some kind of scheduling. ماشي. The data link layer also provides some sensing on the line, whether there is like some transmission on the line, in which case it waits to send a frame over the line and so on, and that also requires some queuing at the data link layer. ماشي. And then the line termination. Line termination is the physical layer. It converts the bits that are going here, it converts the bits to the specific physical representation of the signal, which is appropriate for this type of medium. Like, for example, if it's wireless, I send RF analog signal. If it's Ethernet, I send digital signal, and so on. Any questions? Any? واضح؟ تمام؟ Any questions? طيب, so as we said, the buffering, the arrival via the switches here, as we said, multiple arrivals from multiple input ports might go to the same output port, in which case the switching speed needs to be very fast. So the switching speed needs to be multiple times of the line speed here, because of the fact that multiple input ports may go to the same output port. The queuing delay and loss due to the output port buffer overflow. Of course, we didn't talk about that. So the buffer in the output port may have some packet loss due to overflow. So if the incoming packets are coming with high speed and the flow is the queue is full, then we start to drop the packets. Sometimes this comes from the fact that I get delayed to write on the line because of the fact that the line is busy, and I keep waiting, and then خلاص, and then the queue gets full. So whenever a packet comes in, it will get dropped. Another very interesting phenomena that happens here, which we will talk about, which is called head of line blocking. But before this, what is the, how much is the buffer? So we talked about the fact that we need to have a queue, right? So what is the length? What is the length of this queue? Okay. That's a very critical question. So there are some experimental studies that have provided some guidelines. And by guidelines, I mean that designers may take that as, some guidelines, but definitely to have a specific length of the buffer size, usually they take these guidelines as the minimum amount, and for engineering purposes, they have to design the buffer at least 2 times or sometimes 3 times that particular number, just to be on the safe side. But again, we need to have a length. And we cannot have terabytes of buffer or queue. We cannot have that. So we need to have a limit. So the buffer size is based on 2 things. It's based on the line speed, and it's based on the round trip time. Okay, so some experimental studies, they studied the buffer size as a function of the round trip time, okay, by sending the packet to the ultimate receiver on the line and then receiving a response back. So this is the round trip time. So this actually accounts for the transmission and the propagation delay of the packet, okay. And the actual capacity of the link, which is مثلا 10 gigabit per second. Okay, so they said that the capacity of the queue, or the length of the queue, is simply by multiplying the speed by the round trip time. Okay, because the speed is bits per second, and the round trip time is second. So this means that I get some indication about the length. But is this really the actual size? That's experimental. So some other studies, they said that it's actually the round trip time multiplied by the capacity divided by the square root of the number of flows. And by the number of flows here, I mean that for the input ports, they can go to the same output port. So the maximum number of flows that can go to the same output port, these are n. So I get the square root of n. Again, all of these are experimental studies that provided some guidelines, and these are just guidelines. It's not by any means optimal or exact or something like this. Imagine. So the designers, they take these, as I said, they take these as guidelines, and then they say, okay, so I'm going to design the buffer size at least double this number. ماشي? They take it as a rough estimate. يعني. طيب, a very interesting phenomena that happens, which we talked about when we in network 2 in particular, طبعا, if you remember, which is called head of line blocking. Head of line blocking happens in many queuing systems. Many queuing systems, they suffer from this head of line blocking. So what is this head of line blocking? So imagine, يعني, just as a simple analogy, imagine مثلا if you have a bank and this bank has different doors for people to come in, okay? And people, they line up at these doors. So here, this person, he needs to go to the teller, so he goes to the teller. This person, he needs to go to the customer service, and so on. So that simply mimics the kind of input port to the output port and so on, right? So imagine if a person here and another person here, if that person needs to go to the teller, okay? And another person here needs to go to the same teller, okay? So in that case, that person cannot just go, right? Because the teller now is busy, okay? So the head of line blocking talks about the fact that all the people around this person will be blocked because of the fact that this person is waiting for a service that's currently busy. Even if these customers, they need to go to another output port. And that's the sad reality. يعني if we can get this person كده على جنب كده ندخل الباقيين, they will go faster, right? But we can't because it's a queue, unfortunately. Right? So queue has a single input, single output, right? So this person is blocking everyone behind. So that's the concept of head of line blocking. So imagine if we have these two packets, they are supposed to go to the same output port, right? So if one of them gets switched to the output port, this other one will have to wait because this port now is busy. While the switch fabric finishes all the switching to that output. Again, this output port has a queue, so but I have to switch one packet at a time, right? So if we finish the switching for this packet, we'll go to the second one. But the problem is that while we are switching this packet to that output port, I cannot perform any other switching to that output port until I finish this one. So the problem is that this one will have to wait. By waiting, all these packets behind it are blocked. This is the main problem. All these packets are blocked. ماشي? So this is what we call the phenomena of head of line blocking. Even this one is green, which means that it needs to go here, and that is empty, but unfortunately it's blocked. So this head of line blocking limits the switching speed. Limits the switching speed. ماشي كده? So any question about this? So this is this phenomena comes a lot in any queuing system because of the fact that queuing is based on single input and single output. ماشي؟ طيب خلاص we'll stop here, and then when we come back we'll talk about a very light topic which is based on nostalgia, based on some memories from Network 1. So in the break you better try to refresh your memory from Network 1 because I'm going to ask some questions. ماشي. So now we need to talk about the datagram formats for IP and the IP addressing. For the datagram for IP, this is what we call the IP version 4 protocol suite. Remember we talked about the protocol suite as the group of connecting protocols that work hand in hand to perform certain network function. So if we look at the network layer, we have the IP, of course, the main protocol in the network layer, but IP itself is for packet forwarding, mainly. So IP needs to consult some routing protocols, and routing protocols, as we have discussed before, we have the static routing, dynamic routing, and these protocols, they provide the end-to-end routes. ماشي? So we have some major dynamic routing protocols like REP, OSPF, IGRP, or EIGRP, and we have border gateway protocols and so on. So these are examples for dynamic routing protocols. These are the protocols that try to produce, they produce the routing table according to certain criteria for the best route end-to-end. So the best route end-to-end might be based on the route that gives me the highest bandwidth. Like I need to have, I need to go through the highway because the highway seems to be the fastest. But in certain cases, the highway is not the best route. If the highway مثلا has some traffic jams. طبعا the simplest is REP, so it's based on number of hops and so on. So there are some criteria based on which each of these dynamic routing protocols, they produce the end-to-end route, and based on that they help the router to create and maintain the routing table. And this routing table is used by the IP protocol to forward the packet from the input port to the output port, as we have discussed. And there is, of course, ICMP, Internet Control Management Protocol, which is used for troubleshooting and error reporting, like if we remember the ping and trace route and these kind of application level commands, which uses ICMP to do some troubleshooting to see whether there is a connection end-to-end مثلا with some remote network or some remote server and so on. So together, all of these are what we call a protocol suite, which are protocols that work hand in hand to provide a complete, comprehensive network function. So we'll cover IP protocol first, then we'll talk quickly about ICMP and the other protocols, but very fast. So the datagram for IP, that's how it looks like. Supposedly, you are familiar with this. يعني المفروض this is discussed in details in basic network courses, but يعني really the IP protocol header design gives you some indication about the imperfection of the standard developers. يعني really you will be amazed when you understand the idea behind the IP protocol to see how many, I don't like to call it mistakes, but how many imperfections that have been done as part of IP, although it's the predominant protocol on the internet. So we'll talk about many of these. يعني مثلا version. So they design, this version is basically 4, right? So basically this is, the version is like 4 bits, so this should be 0, 1, 0, 0. So version is fixed. So they thought, okay, so we can have version 4 and version مثلا 5 version, but then when they talked about IP version 6, they found that we have to change everything, صح? We have to change the whole protocol. So they changed everything, okay? So the header length is a field, and from the name, it's the length of the header, which is only the header without the data, right? So why do we need to have a header length? We need to have a length for something that have variable length, right? So having a header length here, if the header has a fixed length, then you don't need that field. And if you go to IP version 6, you see that this field has been removed, because again, out of short-sighted vision, they thought that we need to have a variable size header for IP because we need to account for future upgrades and future functionality of IP. So they thought, okay, so we can have an options fields, and this options fields is like a placeholder for all future implementations and future evolutions of IP. Okay, so these options fields can be used in the future for anything that they did not think about. But of course, so this options fields has never been used, and not only that, in IP version 6 it has been removed. So this options field, it makes the header length varies from 20 bytes all the way to 60 bytes, which means that this is less than 40 bytes. This options field is like 40 bytes, less than 40 bytes. So the maximum size of the header is 60, and the minimum size is 20. ماشي كده؟ But the problem here is that this header length is of size 4 bits only. So how can we represent 60 bytes using a header length of 4 bits? What is the maximum number that we can have using, or we can represent using 4 bits? اللي هو يعني 15 يعني 4 ones is 15 صح ماشي you are right يعني you are close ماشي 4 ones is 15 صح but the maximum size is 16. So how can you do this? So that's the main reason that the IP header is actually organized as 4 byte words. Each of these rows is actually 4 bytes. Okay, this is 4 byte words, and the length here, it actually reports the number of rows, the number of 4 byte words. Okay, so 60 divided by 4 is 15. So the minimum length here is what? So what is the minimum value for the header and the maximum value? The minimum value is when the header size is 20. So what is the number here? And the header length, what number should I put in that case, for the case of 20? 20 bytes is the number of bytes. what is the number of words.
one and one and
لا مش one لا هو the number of bytes is 20. These 20 are organized in terms of 4-byte words, right? So it's 20 over 4, which is 5. So it's 5. So this is 5 in binary. ماشي? So the maximum value is 1111, which is 15, and 15 here corresponds to 60 bytes. ماشي كده؟ طب كده ايه؟ We solved the puzzle of the fact that 4-bit can report the length of the header, and the length exists because of the fact that we have variable length header. ماشي؟ وده this is بقى the field that we have talked about, which is the type of service or differentiated services. They call it type of service or differentiated service, which is divided into ايه بقى؟ لسه قايلها انا. Divided into 2 subfields اللي هم ايه؟ explicit congestion notification and the differentiated service code point. Okay? So again, شوفي how many يعني imperfections. The header length is introduced because of the fact that the header is variable, and it ended up that it's always 5 because the header length is always 20 and the options field is never used. So why did we put أصلا الheader length? They put it وخلاص هو fixed. When you look at the packets inside the internet, you see that all the packets they have 0101. So why do we need to have this أصلا? There's no need, but they have it. ماشي؟ طيب. The type of service, differentiated service code point, and explicit congestion notification. How are these being used? Up to you. Should we use them or not? Up to you. ماشي؟ Optional. Whether you use them or not, you still comply with IP. ماشي؟ طيب. The length is the length of the, sometimes we call it the payload length, which is the length of the header plus the data. And of course, the data part is variable, طبعا. Is variable. So that's why we need to have it. So this is okay. So we need to have a length, because this length is the length of the header plus the data. And since the data part is variable, so we have to report the length here. And this is the length of bytes. ماشي? And because of the fact that we have 16 bits, so we can have flexibility. So the maximum length is 2 to the power 16, which is really high. So we can report the length in terms of bytes. ماشي كده؟ طيب. Identifier, 16-bit, there is a 16-bit identifier. Identifier is similar to a sequence number. So this is an identifier of the packet. Okay? It's similar to the sequence number that we used to have in TCP, right? But is it being used similarly? What do we need the sequence number for the case of TCP? هتفكر؟ ليه؟ Why do we need to have sequence number? Hmm? Missing packet, lost packet. Okay, lost packet. Right. So, as we said, we need. When was the first time we started to talk about implementing or introducing the sequence? Remember, we said that if we have stop and wait, and we have probability of loss, right? Why? Because if the packet is lost, I need to retransmit it. So the receiver needs to distinguish whether this is a duplicate packet or it's a new packet, right? And that's when we started to talk about the sequence, the use of the sequence. Otherwise, we don't need the sequence. If things are moving and there is no possibility of packet loss, why do I need a sequence aslan? So sequence is used mainly for reliable data transfer. But IP is not reliable. IP does not provide any reliability. صح؟ مش IP is based on best effort. So why do we need to have an identifier here? That? Okay, identifier here is not used for reliability in any way. And in fact, if you look at IP version 6, you don't see that identifier أصلا. Interestingly بقى. أصلا actually if you أنا نفسي بس إيه يعني go back to network 1 كده and try to compare the header format of IP version 4 and 6. You see that one of the main objectives of IP version 6 is to really make the header format much simpler. So it's designed based on all the lessons learned from IP version 4. And there is a lot of lessons learned. There is a lot of lessons learned. Identifier, flag, fragment offset. All of these three are being used for fragmentation and reassembly. Those three fields are used for fragmentation and reassembly. Why do we need to have fragmentation? Huh? For queuing? No. No. Not at all.
قلت عشان يبقى fixed length
بس fixed cells ده inside the network switch architecture ماشي بس هنا not necessarily to make the packets of fixed length, but to account for the maximum transmission unit of a certain medium type. ماشي? Because the router may connect Ethernet network with Wi-Fi network or fiber optic network with coaxial network. صح؟ يعني one port may have Ethernet, one port may have Wi-Fi. ماشي? So the input port may have a medium type and the output port may have another medium type, which means that the router here may connect different types of networks together, right? So that one is fiber, this one is wireless, this one is Ethernet, and so on. Okay? But to forward a packet from Ethernet, Ethernet has a specific, what we call it, maximum transmission unit. Ethernet supports packets of length up to 1500 bytes. 1500 bytes. Okay? This is in the standard. Ethernet standard says that the packet length will have a maximum of 1500 bytes and a minimum of 64 bytes. ده بقى network 1 to know why we need to have 64, why we need to have 50. But anyway, we have maximum transmission unit for Ethernet. For wireless, it's less. Wireless supports maximum transmission unit of around 500 bytes. ماشي? But the router needs to route from here to here. So what can I do here? Get from 1500 to 500. So I need to divide each packet into three. We call it fragments, bravo. We call it fragments. ماشي? So one of the functions of the router is to do fragmentation. And of course, fragmentation معناها reassembly. So at the beginning, I need to fragment, and then at the end, I can defragment or reassemble these fragments to get back to the original packet. We'll talk about this in details in the next few slides. طيب. So now this word, this 4-byte word, is used for fragmentation. We have 3 fields for this, which we will talk about. طيب. Time to live. What is this used for, يا جماعة? إيه؟ إيه؟ لا تايم اوت لا يا شيخ لا والعياذ بالله لا مش تايم اوت خالص. حتى time out, do we store time out in the TCP header أصلا? We don't. We don't store a timeout. This is not a timeout.
اللي انا فاهمه ان عشان يكيل اللوبينج باكيتس.
برافو عليك. Yes. So it prevents the packet from looping indefinitely in the network. صح. Okay. But do we use time for this, or we use what?
Number of hops.
Number of hops. برافو عليك. So again, so this is misleading. So it's called time to live. So at the beginning, again, the standard developers, they thought that they can set a timestamp in the packet and then later on detect this timestamp. And then they realized, why do we need to have a time? Because the time cannot be used for this. Why? Because the clock is different from one router to another. So we cannot rely on actual absolute time. And then they thought, okay, so we can simply use the number of hops. So at every single router, what we do is that we get this number and then we subtract one. And by the way, it's in many cases, the Windows operating system, it sets this by default to 256. 256 معناها ايه? The packet at maximum, it needs to go through 256 routers. ماشي? At each router, this will decrement to -1 by -1 and so on until once it becomes 0. Okay, then what do? We drop the packet because the packet has been looping indefinitely inside the network. So again, misleading name, and if you go to IPv6, you will see it called a hop count. Hop count. That's what it should be. But again, short-sighted vision. They didn't think about that. ماشي كده؟ upper layer, this is the upper layer protocol. It refers to the upper layer protocol. Okay, why? Because in the upper layer protocol, IP may deal with, in the upper layer protocol may deal with a TCP, صح? May deal with UDP, may deal with ICMP. So there are a number of these protocols run in the transport layer as processes, software processes in the operating system. They run as processes, right? So I need to send this packet to the particular process based on what? Based on this. Based on the protocol. ماشي كده? So this protocol field exists in the data link layer all the way up to the transport layer. Why? And why do we not have this in the physical layer? Because physical layer is hardware. We don't have processes anymore, right? There's no software processes anymore. I don't need to have this field in the physical layer. It's hardware, pure hardware. From the data link layer, what are the possible protocols in the network layer? There's still IP, there's still X25, ATM, frame relay, MPLS, things like that. So again, all of these, they run, or they have the software, embedded software that runs on the processor. I need to also refer to a specific process from the data link layer up to the network layer. So I need to also provide a protocol header or a protocol header field in the data link layer. Similarly in the network layer, and similarly type in the transport layer, what do we use as a protocol? The port number itself acts as a protocol field that points to a specific application instance. ماشي? What I'm trying to say is that in each of these layers, these protocols, they run as processes. So I always need to have this field to point to which protocol or which process I need to send this packet to, or I need to send this segment to. ماشي? So we need to have this protocol field in all the layers, starting from the data link layer all the way to the transport layer. ماشي؟ طيب. So that's okay. ما فيهوش حاجة ده كويس. طيب. Header checksum is used for what? Header checksum is used for what?
Error detection.
Error detection. برافو عليك. Error detection. So I need to detect مش packet loss بقى هنا. لا, packet arrived but it arrived with some corruption, so I need to detect whether the packet is corrupted or not. ماشي? So the checksum is used for this. Okay? طيب السؤال هنا بقى the router, it runs in the core network, mainly in the core network, and in the core network we talk mainly about wired, whether it's fiber optics or whether it's wired, mainly wired networks. يعني معناها يعني I don't expect مثلا أريد to have inside the network infrastructure to have wireless. Wireless is made for portability, but inside the core network we mainly have one. The question is, what is the probability of a packet being corrupted in the core network? Okay? The answer for this is that they have found that experimentally the probability is next to zero. Packet being lost due to buffer overflow, of course. Packet looping, yes, of course. صح. But what is the probability of a packet being corrupted? Point يعني 10 to the power minus مثلا 18 ولا حاجة. ماشي? That's why in IP version 6 this has been removed. Why? Because they thought that أصلا إحنا unreliable. ماشي؟ خلاص, if there is a problem in the packet, يعني someone else can take care of it, because the probability of having a packet with some corruption is really low in the core network, is really, really low. So IP version 6 removed this. ماشي؟ طيب, source IP address, طبعا this is 32 bits, which we use the dotted decimal notation. فاكرين dotted decimal notation غبية دي? Dotted decimal notation for source IP and destination IP. So the 32 bits are divided into 4 bytes, and each byte is represented using some decimal notation. So that's why we see the IP address like 192.168.1.100 and so on. So this is the dotted decimal notation. طيب, the options fields, as we said, it ranges from 0 to 40, and at all times, almost all times, it's 0. It's always removed. It has never been used. And then the data field, which is valid. So what does the data field contain? This is by the transport layer segment, which is either TCP or UDP or ICMP. ماشي? So here exists the TCP header and the application data and so on. طيب, if you remember, the TCP header was 20 bytes, and the IP header, as we said, the nominal value is again 20 bytes. So we have 40 bytes header for IP and TCP, in addition to the application header, whether it's HTMP, HTTP, or any kind of, or DNS or DHCP, any kind of application level protocol back. We didn't talk about that. We don't have to talk about this. ماشي؟ طيب. So we see how many pitfalls and some imperfections in IPs. Many. And actually, if you look at IP version 6, you see that it's much, much simpler. Header checksum is removed. All these 4-bit words, 4-byte words are removed. ماشي? The header length is removed. Many things have been removed. So the header has become much, much simpler. And not only that, in IP version 6, they thought about adding more logical or more critical functions, something to do with security and so on. Because IP itself does not provide any guarantees, it's unreliable, it's best effort and so on. If you need to provide any extra functionality, you have to have a protocol on top of IP, like ICMP, sometimes IPsec for security, things like that. In IP version 6,
protocol suite.
اللي هي البروتوكول سويت اللي احنا قلنا عليه. In IPv6 بقى they implemented يعني some good features inside IPv6 based on lessons learned from IPv4. تمام؟ طيب هنتكلم على fragmentation and reassembly. So why do we need to have fragmentation? As we said, it's because of the fact that the router actually may deal with different transmission medium or different network technology, like Ethernet, Wi-Fi, fiber optics, things like that. For each of these types of medium, there are some limitations on the maximum transmission unit in terms of size. So the router can potentially, send packets in a particular length, and it has to adjust the length of this packet to fit the transmission medium on the other side. So that process is called fragmentation, and fragmentation requires reassembly. So fragmentation is a critical network function, but it has to be done carefully. We need to talk about some specific procedures that we have to keep in mind when we do fragmentation reassembly. So it looks to us like fragmentation reassembly is a simple thing. خلاص, you have a packet 1500, you need to fit it into 500, then cut this packet into 3 fragments, send them, right? And at a different stage, get the 3 packets, group them into one, off you go. That's it. صح? There are certain precautions that need to be taken into consideration here. One of the things is that first, if we have this is like 1500, this is Ethernet, right? And then we pass through wireless. From Ethernet we came to wireless. So as we said, so we have to provide 3. Each of them is 500. It's not as simple as this. We'll talk about how we do it in details. But the question here is that what if the maximum transmission unit here is back to 2000? If we go from 1500 to 500 and then back to 2000, what do we do? Reassembly. Should we do reassembly or not? What do you think? إيه؟ يعني هو here is 500 and here is 2000. Should we assemble them into one packet as 1500 back, or what do we do?
Because it's within 2000, it will move.
It will move, but should we defragment?
And maybe because it isn't even guaranteed that all the 3 packets will go with the same route. I feel like no, they will just pass as it is.
They pass as it is,
Yeah.
right? So we should not defragment within intermediate routers. Why? You mentioned the reason. Once we do fragmentation, each of these fragments, they become an independent IP packet. Okay? Which actually it may go to different routes. So we cannot, if we want to do reassembly at any router, we cannot. So once we do fragmentation, we never perform defragmentation as at the intermediate routers. We never do that. ماشي? And again, the reason is we're talking about datagrams. Each of these fragments, they become an independent IP packet, which may take different routes. So if we perform assembly here, this means that we have to wait for all the fragments to come. They may never come, because one of them has taken a different route. ماشي؟ طيب. If the maximum transmission unit here is 200, what do we do? We fragment. Okay, so we can perform fragmentation recursively, even as many times as you want. Because fragmentation guarantees that each fragment will become an independent IP packet, right? But we need to maintain where all these fragments came from. Okay? That's why we need the identifier. ماشي? So you can fragment as many times as you want. The reassembly will be done once at the very end. At the end system, not at the intermediate routers. ماشي? At the end system, خلاص, the route has ended. So I should logically wait for all the fragments. طيب, I have all the fragments coming in. They may come unordered. So I have to say, oh, okay, so I need to get this, and group them into one IP packet, then I will send it to the transport layer. صح? Based on what? Based on identifier. So the identifier is needed for facilitating the fragmentation reassembly, not to provide any kind of reliable data transfer, like in the case of TCP. It's not made for this. ماشي؟ واضح؟ Any questions? Okay, so these are things that we need to keep in mind when we do fragmentation. I can provide as many fragmentation process as I need, but the reassembly, it has to be done once at the end system. تمام كده؟ طيب. Now بقى, how do we perform the fragmentation? How do we use the three fields that we talked about to perform the fragmentation? So imagine if we have an IP datagram with a length of 4,000. ماشي? So now the maximum transmission unit for an upcoming network is 1,500. So it's clear that I need to divide the 4,000 into 3 blocks, right? Are they equal size? Not necessarily. I didn't say that, right? So I need to divide them into 3 blocks. I know they have to be divided into 3 fragments, okay? طيب. So now, how do I perform this fragmentation procedure? So first, I have to have the value of the identifier for each fragment, and the value of the flag or fragment flag, and what we call the frag offset. ماشي? So what is the value in each of these fields? The idea is simple. I will eventually group all these fragments based on the identifier, which means all of them need to have the same identifier, logically. So it's the 3 of them will have X. X اللي هي this is the identifier for this particular packet. So all the fragments, they need to have X, so that eventually, whether they arrive in order, they arrive out of order, I need to get all of them, okay, into the packet. So that's the original packet. I need to get all of them into the packet, right? But they may arrive out of order. So it's like a box, and I need, or حاجة box كده يعني, and I need to fit these packets. So where do I fit them? Because they may arrive out of order. So I need to know which one is first, which one is next, and which one is third. صح? I need to have an indication about this. So there's something missing. So the fragment flag is easy. Fragment flag says that this one is not the final segment or the final fragment. So if the flag is 1, this means that this is not the end fragment. There are more coming. And this one is also not the end fragment. This one is the end fragment. So once I get 0, that's an indication for the router اللي هو end system بقى, not the intermediate router, the end system, to say, oh, okay, so the flag is 0. Okay, let me see how many fragments do I get so far. Okay, and hopefully these fragments will fill the bucket of the packets, of the IP packets. ماشي? If not, then it decides about whether there's one missing, because they may arrive on order. There's one missing, or I don't have to wait, so I will drop the whole thing and forget about this packet because I'm unreliable. ماشي? So it waits for مثلا few milliseconds and then it decides whether to drop the packet or not. طيب يبقى اتفضل هنا دلوقتي ايه؟ الفراجمنت offset. Fragment offset is the most important thing because this one is the one that will tell me where should I fit this fragment in the packet. Where? ماشي? Is it the beginning one? Is it the middle one? Is it the last one? So the fragment offset gives you a pointer of where this fragment in the original packet. Where? It points to where this fragment in the original packet. ماشي? So the first fragment naturally will have a fragment offset of 0 because this will have to be put in the first part, which means that it starts from byte 0. ماشي? But the second fragment is based on the length of the first fragment. One thing to pay attention here is that, as we said, the fragments are independent IP packets, which means that each fragment will have a separate IP header, a complete separate IP header. ماشي? So what we do is that 4,000 here is the payload length, and as we said, the payload length includes the length of the header plus the data. So what is the length of the data? صح؟ Excluding 20 for the header. صح كده؟ So it's 3,980. ماشي؟ حد مش فاهم ده جه ازاي؟ فاهم مفهوم؟ تمام. So the fragment offset of the first fragment will be 0 naturally. ماشي؟ Here بقى the fragment offset of the next one is based on the length of the first fragment. What is the length of data of the first fragment? 1,480. صح كده؟ So the fragment offset of the next fragment ماشي should be 1,480. Okay? Ironically بقى the fragment offset refers to the 8 byte words of that fragment, which means that this number should be divided by 8. So that's why here it's 185. 185 is actually 1,408 divided by 8. ماشي? So we have to divide that by 8. And this one is also which is 1,480 times 2 divided by 8, and so on. ماشي? Another thing to pay attention to here is that the 4,000 will have 3,980. We took, the first one took 1,480. The second one took 1,480. ماشي? So the third one will have 1,020, and that's why the pay length is 1,040. ماشي؟ ماشي كده؟ So here it's 185, which is 1,480 divided by 8, and then 370, which is multiply that by 2 divided by 8. تمام كده؟ Any questions? So that's how we perform. So at the receiver side, we can, using these, we go through the fragment offset. Is it 1? Yes. So I better wait. Is it 1? Yes, I better. Is it 0? Oh, okay. So now I can start the reassembly. This is done by the end system, not by intermediate routers. ماشي? Once it's 0, I need to group based on the identifier. I need to group all the fragments and then use the fragment offset to fit the fragments in the bucket. ماشي واضح كده؟ بس this is the fragmentation and reassembly. خلاص خلينا نقف هنا. تمام. So we'll talk very quickly about the IP addressing next time inshallah. Again, this is a topic يعني what I have covered so far is network 1 stuff. It's not and also the IP addressing is going to be network 1 stuff. But we'll talk about something called route summarization, which is not new يعني. But this is an important concept which is used to try to save some sizes in the routing table. We'll talk about why we need to do this. ماشي? We'll talk very, very quickly about ICMP, and we'll not even talk about IP version 6. There's no time for this. But we'll talk about better routing, and in the dynamic routing protocols, I will not try to cover the routing protocols per se, because this is again, this is introductory network stuff. I will get directly to talking about the algorithms that are used by the dynamic routing protocols, which are mainly the Bellman-Ford and the Dijkstra algorithms. These are algorithms that we need to understand how they are done and how to analyze and complexity, how to analyze the complexity of each one, what are the pros and cons for each algorithm and so on. ماشي? So we'll talk about that next time.